Hello everybody, welcome to today's lecture on Maxwell's equations. My name is Riley Campbell and I will be explaining today how we're going to characterize Maxwell's equations in the integral and differential form, and also in free space or vacuum and in matter. Then we're going to apply Maxwell's equations to some sample problems, and finally we're going to demonstrate the interactions between Maxwell's equations and construct EM waves. So to start, we're going to list the Maxwell's equations in free space, starting with Gauss's law. So in integral form, Gauss's law reads as follows. So that is the integral, the closed integral of the electric field dotted with the differential area is equal to the charge enclosed over epsilon naught. In differential form, it reads as follows. That is, the del operator dotted with the electric field is equal to rho, or charge density, divided by epsilon naught. And this is, of course, Gauss's law. This is an important, very, very important equation for electrodynamics and electrostatics. It tells us the strength of an electric field, the magnitude of an electric field. And with this, we can find the value of any electric field that we want to measure. The next law that we're going to discuss is that there is no magnetic monopole. And this doesn't have a fancy name. Some might call it Gauss's law of magnetism. It's very similar, but it's with magnetic fields instead of electric fields. And all it says is that there is no magnetic monopole. In integral form, it reads as follows. The B field instead of the E field, again dotted with differential of the area, is equal to 0. And by that logic, the differential form will read like this. Both are equal to 0, and this tells us very clearly that there is no monopole interaction. A magnet with just one pole does not exist. And that is no magnetic monopole. Next we have Faraday's law. Faraday's law reads as follows in integral form. E dotted with the differential of length is equal to the negative of the derivative of flux with respect to time. In differential form, it reads like this. Del cross, no longer dot, now we're crossing it with E is equal to partial derivative of the B field with respect to time. So this is also a very important equation because it shows us a relationship between the E field and the B field and how it interacts over time. And that is Faraday's law. Finally, fourth of Maxwell's equations is the Ampere-Maxwell law. Now, Ampere's law relates current to the B field, which is very important because, as we know, currents induce B fields. So you run a current through a wire, you get a magnetic field. Now, there was a problem with Faraday's law, and that was solved by Maxwell. And what Maxwell did was he added some additional corrections to it that made it more accurate to reality. And it's a very important part of this theory of electromagnetism. So Ampere-Maxwell law reads as follows in free space. In integral form, the closed integral of B dot dl, so it's this again. However, it equals mu naught epsilon naught d over dt, the integral of E dot ds. It's a little squished. I ran out of room a bit, but that is Ampere-Maxwell law in the integral form. In the differential form, the Ampere-Maxwell law reads as follows. Del cross B, see it's the opposite of the Faraday's law, it's working with B fields instead of E fields, is equal to mu naught J plus mu naught epsilon naught partial E with respect to T. And that is the Ampere Maxwell law. Now, if we combine this with what is called the Lorentz force law, which tells us the force of a field, and it reads as follows. Force is equal to Q times E, the electric field, plus V cross B. We combine Maxwell's equations with the Lorentz force law. We have a complete theory of classical electrodynamics. It shows that all electromagnetic fields are attributed to charges and currents. You can see here, electric fields, we have charges. And down here, magnetic fields, we have currents. So what we're going to do next, and the Lorentz force law shows how these fields affect a charge. So that's this right here, the force of the fields on the charge. So what we're going to do now is take an example of one of Maxwell's laws, Maxwell's equations. We're going to use it to solve a real-world problem. In our case, we're going to take Gauss's law in the integral form, and we're going to solve for the electric field of a charged sphere. So we have a radius of the charged sphere, and then we're going to make what's called a Gaussian surface around that sphere, which has a radius little r. So the radius of the actual metallic charged sphere is big R, and the radius of the Gaussian surface we're using to analyze that electric field of that sphere is little r. And so what we're going to do is we're going to take Gauss's law in the integral form, which is the integral of E dot dA is equal to 1 over epsilon naught times Q, or charge enclosed, the charge enclosed. And so what we can do here is we can rearrange this so that the integral of E dot dA is equal to the integral of the absolute value of E dA. And we can take that and we can say that is equal to the absolute value of E times the integral of dA. Now we have a sphere. If we're integrating just the area of that sphere, that is going to equal to the absolute value of E times the area of that sphere, which is 4 pi r squared. So now we know that the left side of Gauss's law, the integral of E dot dA, is actually equal to E times 4 pi r squared. And that's powerful because what we can do is we set the left side of this equation equal to the right side, and we can solve then for E. And then we're going to do that like so. 4 pi r squared is 1 over epsilon naught Q enclosed. All right? And then if we solve for E, we just divide this 4 pi r squared to the other side, and we get E is equal to, so this is the electric field, is equal to 1 over 4 pi r squared epsilon naught times the charge enclosed. Now, there's one more step here, and that is to put this in vector form. And all we have to do that is add the unit vector r hat. So we have a final answer here using Maxwell's equations to solve for the electric field of a sphere. The electric field is equal to 1 over 4 pi epsilon naught q, because the charge of the sphere is q, or the charge enclosed is q, divided by r squared, we want to relate charge to radius, times r hat, which gives us a direction. It's facing the direction of the radius in spherical coordinates. And that is the electric field strength of a charged sphere solved using one of Maxwell's equations. So next we're going to talk about Maxwell's equations in matter. And, you know, it's interesting because the free space equations do give us a complete theory. We can solve really any problem using the free space equations, but when you have a dielectric material or something that you have a material that reacts to these electric fields and such, and charges, you're going to have what are called bound charges and free charges. And we really don't have any serious control over those bound charges, so we want to get, for interactions in matter, we want to know Maxwell's equations where the bound and free charges are separated. And I'm not going to derive that because that's outside of the scope of this lecture, but I will show you what the results are and what all the parts of those equations mean. So in integral form, when we separate the bound and free charges, and we're really trying to work with the free charges, we get, for Gauss's law in integral form, in integral form, we get the integral of d dot ds is equal to the free charge. And in differential form, we get del dot d is equal to the free charge density. Then for the no magnetic monopole law, the Gauss's law of magnetism, we get the integral of b dot ds is equal to 0, and del dot b is equal to 0. And then for Faraday's law, we get the integral of E dot dl is equal to negative d flux divided by dt, and del cross E is equal to the negative partial of B with respect to T. And for Ampere-Maxwell law, we get the integral of H. This H is called the auxiliary field. Dot dl is equal to I sub f, or the free current, plus the integral of partial of d with respect to t dot ds. So d, as you saw, it's up here too. D is the electrical displacement. And we're going to define the electrical displacement in the auxiliary field in a second. And then so just to wrap this up, the differential form is as follows. Del cross H is equal to J sub F, which is the free charge density, or free current density, plus partial D over partial T. So with respect to T. Now these match up with the free space equations, we have Gauss's law, no magnetic monopole, Faraday's law, and the Ampere-Maxwell law, just like we did in free space. But they're slightly different. And the reason for that is, as we mentioned, we had to separate out the bound and free charges, and we want to work with the free charges. So because of this, we had to insert a couple of things that are not really recognizable from the free space equations, namely the electric displacement, which is D. And so D can be defined, do this in red, D can be defined as D is equal to epsilon naught times the electric field plus P. P is our polarizability, and P is equal to epsilon naught chi of E, where chi of E is our electric susceptibility, times E. So that's what P is there. And then H, our auxiliary field. So D pertains to electric fields. H, the auxiliary field, pertains to magnetic fields. So H is defined as 1 over mu naught times the B field minus M, where M is equal to chi sub M, which is now the magnetic susceptibility, times H. Now we can actually simplify both of these, where if we rearrange the equation, H is equal to 1 over mu times B, and D is equal to epsilon times E. Now epsilon and mu refer to the permeability and permeability, permittivity and permeability. And usually we denote those as epsilon naught, mu naught. Well, those are the permeability and permittivity of free space. In a material, that material is going to have its own permittivity and permeability, which is different than that of free space. And they can be defined as follows. So for epsilon, epsilon is equal to epsilon naught times 1 plus the electric susceptibility. So epsilon naught refers to electric fields. It's essentially how freely an electric field can move through space. Mu is similarly equal to mu naught times 1 plus chi M. And that is how a magnetic field can move through space. So by reorganizing Maxwell's equations and by separating free and bound charges, we have created a powerful tool for solving classical E&M problems in a medium. So we're going to work through one of those problems now. I'm going to erase this. And we're going to try to actually we'll work over here. So the problem we're going to be solving is to find the ratio of conduction current to displacement current in CY. So we are given a frequency equal to 4 times 10 to the 8th hertz. We are given an epsilon equal to 81 times epsilon naught. We are given a mu equal to mu naught. And we are giving a rho, or resistivity, of 0.23 ohms per meter. And the way we're going to solve this is we're going to act as if a parallel plate capacitor with a voltage of V naught cosine 2 pi frequency times t being run through, driven by that voltage, is submerged in the water. And we're going to find the ratio of what is called the conduction current, or J sub C, which is equal to sigma epsilon, sorry, sigma E, and the displacement current, which is equal to the partial derivative of D with respect to T. So the electric field of a parallel plate capacitor can be described as E is equal to sigma over epsilon, which we can equate to the charge divided by epsilon times area, which is equal to V over D, voltage over distance. So we know that D, which is in our displacement current, is equal to epsilon times E, as we discussed over here. And sigma, or the conductivity, is equal to 1 divided by the resistivity, rho. And so, to solve this, we now just need to basically plug and chug. We have J sub C, J sub D. We got to solve for J sub C as follows. So J sub C to sigma E, which is equal to 1 over rho times the electric field, which is equal to 1 over rho times V over D, which is equal to 1 over rho times V naught cosine of 2 pi frequency T divided by D, which is finally equal to V naught cosine 2 pi ut divided by rho D. So now we have our conduction current. Now we need to solve for our displacement current, and then we're going to divide the conduction current by the displacement current to solve for the ratio. So J sub D is equal to partial D over partial T, which is equal to T times epsilon E, which is equal to epsilon times the partial T of E. So we're going to just pull E from where we already have it solved. We pull the 1 over rho. We know it's V naught cosine 2 pi mu T over D. So we're going to plug that in to our partial derivative here. When we solve that, we get negative epsilon V naught 2 pi mu sine of 2 pi mu T divided by D. And so now we just want to divide this by this. When we do that, we get this as our result. J C over J sub D is equal to 1 over 2 pi mu epsilon rho. When we plug our values from up here into that, we get a ratio of 2.41. I didn't really have to erase the old example, but for this new example, we see that we can successfully solve any problem we want using Maxwell's equations. You can see we used displacement, we solved through, and we got a result of 2.41 as our ratio for our displacement and conduction currents. So now that we have a model of electrodynamics and have shown that it functions for both problems in a vacuum and problems in matter, it is important to observe how these functions, note, of nature interact with each other. To do this, we are going to look at the formation of electromagnetic waves. And so to do that, I am going to have to erase this. All right, so to study the interactions between Maxwell's equations with each other, we're going to have to take a step back to the free space equations. So what we're going to do is we're going to study E and M waves in a vacuum. And to do that, we're going to set up two partial differential equations. And those are going to be as follows. So we're going to take, in free space, del dot E is equal to 0. We modified it a little bit. There is no charge density in this situation. And del cross E is equal to the partial of B with respect to T, of course negative, just like it's written over there, Faraday's law. Then we're going to take del dot B is equal to 0, no magnetic monopole, and del cross B is equal to mu naught epsilon naught partial E partial T. This is Ampere Maxwell law, except we removed the mu naught J term from it. So this is now a system of partial differential equations. And when they are solved, again, now solving partial differential equations is outside the scope of this lecture, but when they are solved, we find two second order partial differential equations. Mu naught, epsilon naught, partial E, partial T, and same thing for the magnetic field. All right. So this satisfies the standard general three-dimensional wave equation, which is as follows. F is a function, is equal to 1 over the velocity squared times the second order partial of F with respect to T. You can see there's a parallel here between these and this. So what we can gather from this is that in this three-dimensional wave equation, 1 over v squared is equal to mu naught epsilon naught. We're going to write that up here. 1 over v squared is equal to mu naught epsilon naught. If we rearrange this equation, we get v is equal to 1 over the square root of mu naught times epsilon naught. These are the same thing, rearranged. So mu naught and epsilon naught have a known value. Mu naught is equal to 4 pi times 10 to the minus 7 henries per meter, and epsilon naught is equal to 8.854 times 10 to the minus 12 farads per meter. If we plug these numbers into this equation, we get a velocity of 2.99796 times 10 to the 8th meters per second, speed of light. So what this implies is that E and M waves move at the speed of light. Electric fields, magnetic fields, the field going through your light bulbs, your cell phone, they're all moving at the speed of light. But what this also implies is that perhaps light itself is an electromagnetic wave. Furthermore, we're going to say that these waves are sinusoidal, and they have a singular wavelength and corresponding frequency. These are called monochromatic plane waves. We're also going to say that it is moving in the z direction with no x or y dependence. So that's going to look like this. X, y, z. That is a singular monochromatic plane. Waves like this come in the following form. They come in this form for electric and magnetic fields. We have E as a function of Z and T. So the Z direction and a function of time is equal to the electric field naught times E to the I times Kz minus omega T. And the same follows for the B field. Well, because there is no magnetic monopole, and in this situation, no electric monopole, we can say that E naught sub Z is equal to B naught sub Z, which is equal to 0. And this is going to show mathematically that EM waves are transverse, which means they are perpendicular to the direction of propagation. As you can see, we're moving in the Z direction, and they're perpendicular to that Z direction. Perpendicular. But furthermore, Faraday's law shows us a relationship between the magnitudes of the electric and magnetic fields. That relationship is as follows. Negative K times E naught sub Y, so in the Y direction, is equal to omega, or the angular frequency, times B naught in the X direction. And similarly, K times E naught in the X direction is equal to omega B naught in the Y direction. This can be simplified to this. B naught is equal to K over omega times Z hat, the unit vector Z, crossed with E naught. This means that not only are EM waves transverse of the direction of propagation, they're not just perpendicular to the direction it's moving, but they are actually perpendicular to each other. Their real amplitudes can therefore be expressed as follows. B naught is equal to K over omega times E naught, or 1 over the speed of light times E naught. So if E points in the X direction, B will point in the Y direction. Skipping a lot of derivation in math, we get the following two functions. Put them down here. This is kind of our final result here. We're wrapping it up. E times Z sub T, function, E is a function of Z and T, is equal to E naught cosine of Kz minus omega T plus delta function in the X hat direction. And B, similarly, Z sub T is equal to 1 over C, B is equal to 1 over C, times E naught, times the cosine of Kz minus omega T plus a delta function in the Y hat direction, the Y unit vector direction. And so, if you know a little bit of mathematics, you know that we can separate, we have the imaginary part I in these original wave equations. We can separate those out and they become cosine functions. And so the math, if you can imagine it, follows from this to this through this, right? But what's really cool about this is what we get as a result, graphically. So here, as I drew earlier, we have our simple monochromatic plane wave. We are going to describe this sinusoidal wave, which is propagating up in the x direction and moving in the z direction, as our electric field wave. Because the magnetic field wave has to be perpendicular to that, we can describe it as such. Moving in the little difficult to draw. Y direction. That's not the best drawing of it you've ever seen, but that is our B field in red, and that is our E field in blue. And they are moving towards you like this. And that is light, which has all been derived from Maxwell's equations. Though not by me, I kept it simple as I could. We were able to get light waves in free space in a vacuum, how they move through outer space from Maxwell's equations. Thank you very much. That's all I have for you.